Hello, everyone. I'm Tian from Washington University in St. Louis. Today, I'll be introducing our work in preparation in collaborating with James Mertens, Matt Kenny about metric reconstruction from Lightcones. So reconstructing metric might be an interesting and useful topic because we will know how to correct our cosmic observables. So our cosmic observables need to be corrected because either of some general relativistic effect or because some interaction between photons and baryonic matter. For example, we know that cosmic photons before arriving Earth are experiencing some Weaklensing effect, which means that the bundle of photon will be deflected so that it will bias our interpretation to the angular diameter of any object, and it will also introduce some shear terms. And another well-known effect is ISW effect. It says when the photon is traveling inside some gravitational potential well, and if that gravitational potential wells are having some time dependence, and it will either redshift or blue shift the photon traveling through it. Another possible correction might come from interaction between photons and baryonic matter. For example, when considering that photon interaction with kinetic electrons in our universe, we call it KSZ effect. It turns out it will provide some potential bias to your interpretation to the lengthening of CMB, although only at very high multiples. Another very useful techniques you might rely on this KSZ effect is called KSZ tomography, and it turns out it will, by cross-correlating CMB and the large-scale structure data, it is very useful interpreting many cosmic observables. Another interesting aspect when talking about cosmic observable is how to extract cosmic observable from our simulation. For example, when we are simulating the evolution of large-scale structure, we actually involve a 3D hypersurfaces from high redshift to low redshift, and we basically solve Poisson equation at each constant redshift within this 3D periodic box to get the gravitational Newtonian potential. And however, the real universe we are observing is actually a Lightcone, and we usually think that the linearized GR theory might better describe the dynamics on that Lightcone. And within the linearized GR theory, we can write down, and after fixing the gauge, without assuming an isotropic stress and only focused on the scalar perturbation, we can write down our metric in the simple form has only 1 degree of freedom of budding potential phi, and this phi follows a slightly more complicated equation of motions. So the question is, can we reconstruct the metric component following linearized GR theory on that Lightcone, because the Lightcone might be more close to is closer to our observation. And we want to this procedure, if we can do it, we want to this procedure work as post-processing so that it will work with any unbodied data generated by different simulations. And we want to make it work with, to be able to work with both snapshot and Lightcone data, so that can be universal to any generalized embodied data. And we want to find the exact solution to the linearized GR theory to account for all the GR effects. So things we would like to find the solutions to linearized gravity theory by post-processing the Newtonian simulation data. The first thing we have to do is to find the mapping between the Newtonian gravity simulation to the linearized GR theory. Luckily, previous study shows us a very simple dictionary that is able to map between Newtonian gravity simulation and GR theory. And according to this dictionary, we just need to modify a little to the particle position given by the simulation so that the data inside the simulation can represent the data, that solution in the linearized GR theory. And this modification turns out depend only on the initial condition and usually only manifest at large scale. Another way to interpret this dictionary is from the gauge perspective. Other studies basically saying that other study basically show that the result of Newtonian simulation can be interpreted as the result in general linearized GR theory within the so-called n-body gauge. But luckily, we have correspondence between Newtonian gravity simulation and linearized GR, which suggests that we might be able to reconstruct the metric perturbation component from in the sense of linearized GR and from the Lightcone. In order to find the solution to the linearized equation of motion on the Lightcone, the first thing we need to do is to discretize the data on some mesh. So we choose to work with some spherical coordinates like on the Lightcone data like this. So I'm showing here a polar coordinate projection, but actually to deal with the 3D Lightcone data, we have to build a 3D spherical coordinate mesh. And the difficulty is that even if we have the mesh, we have the data, it is still hard to solve the Laplacian equation on the spherical coordinate, especially the first equation here. Our goal is to look for the solution to this complicated linearized GR equation after taking the data from the n-body simulation. Since it's complicated, we choose to rely on some trick on coordinate transformation. So it turns out we could do coordinate transformation like this, basically trivial transform the regular conformal time and the mixing transform the radial direction of the regular spherical coordinate. So after knowing the relationship between the coordinates, we can also write down the coordinate transformation for the partial derivative very easily, and further define the new time direction by setting up the partial derivative along the time direction, and define a new radial direction by defining a large pi and set it as a phi prime. So to interpret this coordinate transformation, we can actually find analogy in a so-called Lightcone coordinate. So the Lightcone coordinate is very useful coordinate system when we are analyzing any null geodesic property, when we are analyzing, for example, the Lightcone. So with this Lightcone coordinate, for all the data on this Lightcone has the same W coordinate, which is W coordinate here. And it turns out that the radial direction, the partial the radial partial derivative direction is coincide with the radial direction on the corresponding hypersurface. So that turns out to be very good property for the Lightcone, because when you are analyzing the light rays, they don't change the radial direction, they only change the time direction and the angular direction. And the regular derivative to the original conformal time can be decomposed as the combination of the new time, combination of the partial derivative of the new time coordinate plus the radial partial derivative. So that's the fairly good property of this new Lightcone coordinate. So after knowing the transformation, after fixing the coordinate transformation, we can massage this these three equations, and by disentangle the Laplacian term and plugging the second and third term into the first equation, and finally gets the two new equations. So although it looks complicated, those two new equations have a very better property. So if you look at the equation 1, it is actually a elliptical second order elliptical linear equation, and although it contains still angular Laplacian, but since it's linear, we can rely on spherical coordinate. We can rely on spherical decomposition, harmonic decomposition, so that we can choose to work only in the LM space, so we don't have this derivative anymore. And then what left us is a regular elliptical linear equation. Although it coupled to the equation 2 is still linear and still linear order, and can be solved very easily by time integration. However, in practice, when we are looking for the solution to these two equations with Newton iteration, a common problem is that most of the time the convergence speed is very unsatisfactory. And especially when we are dealing with large-scale structured data, we want our angular resolution, radial resolution. We want to have very high angular resolution and radial resolution. In that case, it is not acceptable to have such a slow convergence rate. So a technique that is actually very useful, is actually very widely used in any relaxation scheme, is called multigrid method. So that's the scheme we can rely on to speed up our relaxation scheme. The multigrid method is the idea is very similar to the adaptive mesh refinement, but it is actually the inverse adaptive mesh refinement, because usually with MR, adaptive mesh refinement technique, you have your courses level, and all the level above it have finer grid, has higher resolution. But here you are working with your best grid, which has the highest resolution, and for any grid below it, it has the lower and lower resolution. So idea is that you basically relax some step so that you get some data, and on cursor level, it's solve a so-called correction equation so that it provides the data. So it will correct the equation on its parent level. And you can do this procedure recursively so that the level 1 corrects the result on level 2, and level 2 corrects the result on level 3, so that the overall convergence speed will get speed up by a lot. Because those cursor levels are having much lower resolution, the convergent speed on that level will be much higher than the final level. And in practice, when implement this procedure, you can choose to work with so-called V-circle, where you start with your finest grid and go to a cursor grid and do some several relaxations and go to a cursor grid. And once you hit your courses the grid, you can get almost the perfect solution because it's two course. And you use the data on this level 0, correct the result on level 1, so that if that correction turns out to be a good correction, the level 1 the solution accuracy on the level 1 will jump to a fairly amount, to a large amount. And after doing several relaxation on level 1, and it provides correction to the level 2, and you can do that recursively. And in practice, you can also choose to work with W circle, so you don't do you don't hit the bottom at the beginning. You gradually hit the bottom. But those are the tricks, and sometimes they are helpful, but sometimes they are not. And it turns out in our case, the usually V circle, the regular V circle, works already very well and can help us a lot and speed up the convergence rate by order of magnitude. That makes it possible for us to solve the equation on the Lightcone with relatively high resolution. So to summarize our methodology on reconstructing the metric component from the Lightcone data. So first, we take some Lightcone data and build the mesh on that, and build our spherical coordinate mesh. The way we build our spherical coordinate mesh is discretizing the radial direction according to the uniform co-moving distance. And on the angular direction, our discretization relying on the Hughes grid, so that each angular pixel has the same area. And after discretization, we basically decompose the Lightcone data, the Lightcone particles, so that to generate the delta field on the Lightcone coordinate and the velocity, the peculiar velocity field on the Lightcone coordinate. And after we have all the matter component information, we take one snapshot at high redshift and another snapshot at low redshift, get the potential data and the pi field, which is the radial derivative data on both snapshots, and take those as our boundary terms. so that based on those boundary terms, we will be able to relax the solution between those boundary terms. And the way we relax solution is relying on the multigrid method, so that coarser grid will speed up the solution on the final grid so that achieve satisfactory convergence speed for the whole Lightcone coordinate. After constructing the phi field data, the Barling potential data on the Lightcone coordinate, the next thing we could do straightforwardly could be, for example, calculating the lensing term or shear term or SW term by following the grid line directly, because if that is so-called Born approximation, it says that if that is so-called Born approximation, which assumes that light travels according to the straight line, and which represents the trace of the light of the coordinate grid. However, we can do the next step. We can expand to the next step by tracing the rays exactly on the Lightcone coordinate. It means that we should follow the photon, and the deflection angle of the photon can be calculated by interpolating between the Lightcone coordinates. So in principle, we can do that, and by tracing the photon, we can also calculate the lensing convergence, the shear term, and also evaluate the redshift perturbation. We have implemented the procedure I mentioned before. Here, I would like to give some preliminary results and some tests to this procedure. So first of all, we need to decide how we're going to get our Lightcone data. So in principle, this Lightcone data generated by simulation can be generated by on-the-fly n-body simulation, as long as the n-body code supports doing that. And it can also be generated by post-processing the snapshots data. And from our test, we didn't, so those two methods are comparable. They are generating almost the same result as long as you have enough snapshots to generate the Lightcone data. And we did so, and the first test we have done is to test the ability of this scheme in restoring the true potential value. So we try to run some n-body simulation with a resolution of 1,000, and we pick our radial resolution when we are building our coordinates, our spherical coordinate, our Lightcone coordinates as the comparable resolution, and choose our n side to be 512. And we basically build a Lightcone data from 16 snapshots, so it's not so many snapshots. And we implement this procedure I mentioned before and build the Lightcone, and the build Lightcone covers the redshift range between 0.03 to 0.5. And then we pick a slice from it and generating the potential value of it, and compare to the real true value generated by n-body simulation. So when I run n-body simulation, I choose to output a snapshot at the same redshift and compare these two, and turns out they are almost the same, and at least there is no difference at all in their power spectrum. They look the same, and at least they are not differentiable from their power spectrum. Another test we have done about this new scheme is to look at the Weaklensing data. So basically, we generate the Weaklensing data by ray tracing inside our Lightcone coordinate at redshift z equals 5, and compare it to the Born approximation method or linearized or linear theory. So here I'm showing the plots of lensing power at z equals 0.5. I'm comparing the lensing power generated by the ray tracing techniques to a thin lens approximation, which is basically Born approximation, which is actually assuming Born approximation, and the lensing power is generated by convoluting some kernel with with the density contrast of the Lightcone particles, and they coincide very well. Usually, they coincide very well, which suggests that the correction of post-Born is very small and negligible, and some other study also, which is consistent with results suggested by other studies. Another test we could do is to test the lensing power generated by this scheme. So here I'm showing the result of the lensing power generated by this new scheme at z equals 0.5. I'm comparing the lensing power generated by directly tracing the rays with the lensing power generated by Born approximation and thin lens approximation, so that by assuming thin lens approximation, we can calculate the lensing power by convoluting some kernel with some density contrast on the Lightcone. So these two methods turned out to coincide very well, and suggest that the post-Born effect for most of the time is negligible and is consistent with the results suggested by other studies. And both of the methods coincide with the linear theory, except for the low L, which is low L side, which is limited by the box side of our simulation, and also on the high L side, which is the which get a large separation because of the finite resolution we are relying on. Another test to this new scheme could be ISW effect. So compared to the lensing effect, ISW effect is slightly harder to extract because it involves the time integrating the time derivative of the gravitational potential. And most of the simulation won't store this quantity, but our scheme is able to restore the ISW power, which is linearly coincided with linear result very well until L equals 50 or 40. And after that, the nonlinear effects start dominate, and the result is deviating from the linear result. So to summarize, it is possible to reconstruct this Lightcone metric component under Newtonian gauge with assuming only scalar perturbation without anisotropic stress by post-processing n-body Lightcone data. So the Lightcone data used for construction can be generated either on the fly or restored from n-body snapshots. And turns out we don't need so many snapshots to generate accurate Lightcone data, and which can be used to generate the metric component data. So based on the ray tracing through Lightcone grid, we can calculate the lensing term or SW term power, and so we can estimate the lensing or SW power or other general relativistic effects. So the first, in the future, we would like to see if this method can give us the accurate description to the high order terms, high order GR terms, and also we want to ask how this scheme can be combined with the popular KC tomography to give high order corrections. And finally, our final question mark is about how this method, if this method is able to be applied to our real cosmological data, and if this is gonna be helpful in interpreting, in restoring the real cosmic observables, cosmic metric components from our real data. So that's all about today's talk. Thank you so much.